Hello and welcome to our mathematics lesson. We continue to tackle the topic on properties of geometrical figures. During our last lesson, we were able to cover two subtopics in this particular topic. One, we were able to look at angles and triangles. Then two, we were able to look at parallel lines. Now with these angles and triangles, we were able to say that an angle is formed whenever we have two lines or two line segments meeting. So that point of meeting will form a particular angle. And we said there are different types of angles depending on the measurement of their sizes. Those which are less than 90 degrees, we said they are referred to as acute angles, while those which are more than 90 degrees but less than 180 degrees, we are able to refer to them as obtuse angles. We also said we have got different types of angles, like when you talk about a right angle, which we said measures exactly 90 degrees. We are also able to look at angles at a point which we said form 360 degrees. Then on the issue to do with the triangles, we say that a triangle obtains or derives its name from tri, meaning three. That is, we have got three sides that are making up a triangle. And that means a triangle has got three sides, same with three angles. Some of the angles of a triangle, we're also able to say that they add up to 180 degrees. And again, depending on their shapes, we have got different types of triangles. Like we mentioned of a scalene triangle, which we said all the sides and all the angles are not equal. The opposite is an equilateral triangle. In an equilateral triangle, all the angles and all the sides are equal. We are also able to mention about that kind of a triangle which has two sides equal and the base angles equal and two of its sides are equal. And we were able to refer to it as an isosceles triangle. Then you have got, of course, the one that measures 90 degrees, which is a right angled triangle. So depending on the sizes of the angles, we can have those kinds of triangles. And then on parallel lines, we said parallel lines are lines which when drawn, they'll never meet at any particular point. And we normally denote these parallel lines using special arrows. So this indicates that these two lines are parallel. We talked about a line that crosses through these two particular parallel lines to be called a transversal. This particular transversal cutting across these two parallel lines forms a number of angles. We have this angle, we have this angle, we have this angle, we have that particular angle. We also have got these other angles formed. And we said depending on their positions on those particular parallel lines, each one of them have got its individual name. Like we talked about this as being referred to as co-interior angles, which normally add up to 180 degrees. We talked about A and B as being vertically opposite. We talked about B and C, F and G as being alternate angles, and they are always equal. Angles at this particular point will always be equal to 360 degrees. We were also able to check or look at how questions can come on how we can be able to calculate angles on these two parallel lines and a transversal. And also we were able to look at how we can be able to complete an angle if it is missing in a triangle. Then for the right angle triangles, we are also able to look at how we can be able to calculate a side by use of the Pythagoras theorem. During this lesson, we want to look at another subtopic of this particular topic called quadrilaterals and other polygons. So this is what we shall be covering during this lesson. Now from the word itself, quadrilateral, it is synonymous that we are talking about something that is in quad. And whenever we mention a quad, like a quadruple animal, we mean something or an animal that has got 4 legs. A toddler or a young child will always walk in 4. That is by use of the hind limbs and also the hands. So we can be able to say that that baby or the toddler is walking in quadruples. So quadrilaterals is simply a figure that has got 4 sides which are joined together continuously. And given the 4 sides that are forming up a quadrilateral, we can have a variety or a large number of different types of quadrilateral. That is to say that figures that have got 4 sides are so many in nature. That is what we shall be looking at under this quadrilateral. The most important thing concerning this quadrilateral is that sometimes you can have convex quadrilaterals and non-convex quadrilaterals. When we talk about convex quadrilaterals, we talk about a quadrilaterals where all those particular angles will be less than 180 degrees. But for the non-convex one, you will find that at least one of the angles in that particular figure or shape is more than 180 degrees. So we might say that concerning the quadrilaterals that quadrilaterals are 2-dimensional shapes. They are 2-dimensional shapes with straight sides, and these sides are 4 in number. Then for the polygons, we can also be able to describe polygons in the same manner, that it's a 2-dimensional shape or figure that has got straight sides. 4 not in question now, because we have got different types of polygons dependent on the number of sides. We have convex polygons. So first, polygons are also 2-dimensional shapes with straight lines or what we might be able to say they are straight sides. So that is just any particular polygon. So in that particular case, if you look at any polygon, depending on the number of sides it has or the number of lines that is forming that particular shape, then it will derive its name from there. And we are going to look at the different names that are given to different polygons. Another issue on the same is about the convex aspects. We have got convex polygons, and with the convex polygons we have all the interior angles. They have all the interior angles less than 180 degrees. And another point on the convex polygons is that when you draw the diagonals, they are going to intersect or meet inside that particular polygon or quadrilateral. So we are saying that diagonals of convex polygons intersect inside the polygon. They intersect inside the polygon. So assuming that this was our polygon, for example, and in this case we are taking the case of a quadrilateral which has got 4 sides, then if you were to measure, all these angles will be less than 180 degrees. And again, if you are to draw the diagonals, you'll discover that they'll meet inside that particular shape. So the two are opposite for the non-convex polygons, which you want to see. One is that a non-convex polygon has at least one interior angle more than 180 degrees. So if you are to measure the size of that of the angles that are forming or that are making up that particular polygon, you'll discover that at least one of the angle is greater than 180 degrees, and that will give it its convex nature. Another point is that the diagonals of a non-convex polygon meet outside the shape or figure or that particular polygon. We can have a good example of a quadrilateral as this, which you can be able to say still has got 4 sides. 1, 2, 3, 4. This is straight. But if you look, if you were to calculate or measure the size of this particular angle, you will discover that it's more than 180 degrees. And if we were to get the diagonals, this will fall automatically outside, because we can have that joint to that, and these are the joint to the other one. So you'll discover that the diagonal will be outside, and will be outside that particular shape or that particular figure. So we now want to develop a table in which we are going to name the polygons depending on one, the number of sides they have, and also the number of triangles making them. But on the number of triangles making them, we shall be interested in finding out how what is the size or what is the total sum of the interior angles of these particular mentioned polygons. So as we previously said, a triangle will only have 180 degrees. So what if you have another polygon that composes of more than one triangle? Let's say it has got two triangles. Then that will automatically tell you that that figure will have a total of 360 degrees internally. We have a special formula for calculating the size, the sum of interior angles of a polygon that has got n sides. The formula says that the sum of interior angles of a polygon is given by, now that sum, you can call it S of n sided polygon is equals to 4n minus, it should be 2n, is equals to 180 into n subtract 2. That means for you to get the sum of interior angles of a polygon, you take 180 into n minus 2. Alternatively, you can use the number of right angles that are forming that particular polygon, and that means you will have a right angle outside, then you can be able to filter the 2 inside. So this will be 2n subtract 4. So these two formulas are normally used whenever you want to find the sum of interior angles of a polygon. For example, a triangle, it's a three-sided polygon. We have previously learned that a triangle has got 180 degrees. Can we be able to confirm that with this? So n stands in for the number of sides. So let's see. A triangle has got 3 sides, so n is equals to 3. So this will be 180 into 3 minus 2. This will be 180. 3 minus 2 is 1, and this will give us 180 degrees, which indeed is true, that a triangle has got 180 degrees inside or internally. Still, this formula is applicable. 90 into 2 multiplied by 3 subtract 4. This will be 90 into 6 subtract 4. This will be 90 into 2, which will still give us 180 degrees. So you discover that these two formulas are speaking truth about the sum of interior angles of a polygon. So we're going to make good use of them as we shall be looking at the different types of polygons. So we have that table where we shall have the polygon on the first column, the number of sides constituting, number of sides that are constituting that particular shape, and then the angle sum, which is S. Now the first polygon which we have been able to look at is the triangle, and for the triangle we have said it has got 3 sides and it has got only one right angle, and that means its sum of its interior angles will be 180 degrees. The next one is a quadrilateral. A quadrilateral, we said, has got how many? 4 sides. So the number of sides constituting a quadrilateral are 4. And inside that particular quadrilateral, we are going to have 2 triangles. I wish we could have had a column for number of right triangles. Here is 1. So this one will have 2 triangles, and if it has got 2 triangles, that will mean that the sum of interior angles is going to be 360 degrees. Number 3 is the one that has got 5 sides. It's normally called a pentagon. A pentagon has got 5 sides, and therefore if it has got 5 sides, that means it's going to have how many triangles? It's going to have 3 triangles. And if there are 3 triangles, that will be 180 multiplied by 3, which will give us 540 degrees. So sum of interior angles of a pentagon is 540. Number 4, after the pentagon, we have one that has got 6 sides, which is called a hexagon. A hexagon has got 6 sides, and the number of triangles again will be 6 minus 2, or simply we follow that particular order, which means it will be 4. So that means the sum of interior angles is going to be 4 multiplied by 180, which will give you 720 degrees. So the sum of interior angles of a hexagon is 720 degrees. Number 5, we have got one that has got 7. It's called a heptagon. We are saying it has got 7 sides. Number of triangles, 7 minus 2, which will be 5. Number of the size of interior angles, 5 multiplied by 180, which will give you 900 degrees. Therefore, a heptagon has got 900 degrees internally. Number 6, we have one that has got 8 sides. It's called an octagon. We are saying it has got 8 sides. Number of triangles, 8 minus 2, which will be 6. And therefore, size or sum of interior angles will be 6 multiplied by 180, which will give us 1080 degrees. And this will tell us that in an octagon, it has got 6 triangles, and each triangle is 180 degrees. Therefore, internally, it's going to have 1080 degrees. The 7th, we have got the one that has got 9 sides. It's called a nonagon. Nonagon. It has got 9 sides. That means it's going to have 7 triangles. And therefore, 7 multiplied by 180 will give us 1260. So this tells us that the sum of interior angles in a nonagon is 1260 degrees. The last one is the one that has got 10 sides. We call it a decagon. A decagon has got 10 sides, and therefore the number of triangles will be 10 minus 2, which will be 8. 8 multiplied by 180 will give us 1440. 1440 degrees. So these are the most common polygons that we might have: quadrilateral, triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. Each of them has got those particular size, sum of interior angles. And we have said it actually depends on the number of triangles that are forming that particular polygon. If it is 3 triangles, then you multiply 180 by 3, which will give you 540. Now we have got 2 other ones which we are just going to mention. The one that has got 11 sides. The one that has got 11 sides derives its name from a decagon, and it's called andegon. And decagon and decagon. It has got 11 sides. Then we have the one that has got 12 sides. It's called dodecagon. The number of triangles making up an 11-sided polygon will be 9, and therefore when you take 9 multiplied by 180, you'll get 1620. So it has got 1620 degrees. Then for the dodecagon, which has got 12 sides, it's going to have 9 triangles, and therefore the total angles will be 1800 degrees. Then we have got a general now, an n-sided polygon. An n-sided polygon will be called an n-gon, and the sum of the interior angles of an n-gon will be equivalent to this, which is 180 into n subtract 2, or simply 90 into 2n subtract 4. So the 2 are usually used. So this is a good table demonstrating all those types of polygons and the quadrilaterals and the sum of the interior angles. We have said the most important thing is for you to know that the sum is derived actually from the number of right angle triangles inside that particular polygon. So that was concerning interior angles. We want to look at a case of exterior angles. Now polygons, whenever drawn, like you can have, I'm assuming that these are regular shaped pentagon. So we can be able to recall it's a 6-sided figure, therefore it's going to be an hexagon. You can be able to recall when we were looking at a triangle, we said we can be able to form exterior angles by extending the sides. So when you extend, you form exterior angles. And from the calculations that we were able to make, we were able to say that the sum of exterior angles of a triangle, that is A plus B plus C, will be equal to 360 will be equal to 360 degrees. Let's see for the case of other polygons. Now, if this is a regular hexagon and we want to determine the number of exterior angles it's going to have, then it is very simple. Each side exterior angle. So we extend these particular sides, they'll form exterior angle. Extend this side, it forms an exterior angle. Extend this side, it forms an exterior angle. Extend this side, it forms an exterior angle. extend that side, it forms an exterior angle. So given that this is A, B, C, D, and E, those particular angles will be referred to as exterior angles. So angles A, B, C, D, and E are exterior angles. Now there's something else you will discover later on concerning these exterior angles, and is that sum of exterior angles of polygons add up still to 360 degrees. Therefore, if you are to take the sum of A plus B plus C plus D plus E, it will simply give you 360 degrees. And therefore, we can be able to say that sum size of an exterior angle, so long as it's a regular polygon, will be given by 360 divided by n, or number of sides. Number of sides that are constituting that particular polygon. Because as you can be able to see, these are 6 sides. So in case you want to get, if it's a regular polygon and you want to get the size of each exterior angle, then we are going to take 360 divided by n, and our n is 6. So this will give us 60 degrees, and that means each of them is going to be 60 degrees. That means from the knowledge of the exterior angles, you can be able to get the size of interior angles, because that will be a straight line. And straight lines or angles on a straight line normally add up to 180 degrees. So adding or lessing 60 from 180 will give you 120. And given that it's going to be a regular hexagon, all the interior angles are going to be 120 degrees. Still, you can be able to get the sum of the interior angles by either summing all these angles, or we use the formula. Now we have got the cases of regular polygons and irregular polygons. For the regular polygons, all the angles and all the sides are going to be equal, which is different case with an irregular polygon, where you'll find that not all the sides are equal. Maybe 4 out of the 5 can be equal, or totally all of them are of different measurement. And if they are of different measurement, then that will tell you that each of the interior angles is going to have a different size of an angle. But that does not affect the whole concept of the exterior angles, because still, whether it was regular or irregular, the sum of the exterior angles of any polygon should add up to 360 degrees. So regular polygons have equal lengths of sides and interior angles. They also have equal interior angles. We have got a class of quadrilaterals called parallelograms. Then we have another one called the kite. Then we have got now the rhombuses. We like to mention about those different categories quickly. Parallelograms just as the name suggests, parallelogram. That means at least a pair or all the pairs of the sides that are constituting that particular figure must be parallel. So you can be able to say that parallelograms are quadrilaterals they are quadrilaterals with two pairs of parallel lines. So here the clarification is very clear that for us to be able to have a parallelogram, we must have two pairs of what? Parallel lines. So that will now take out the concept of the issues to do with the trapezia, which we know have got only a single pair of parallel lines. So a good examples of these particular parallelograms which have got two pairs of parallel sides. One is the parallelogram itself. The parallelogram itself, which we understand is that we're going to have two pairs of parallel lines. These and these are parallel, these and these are parallel. So that constitutes two pairs of parallel lines. And if you were to draw their diagonals, then this side will be equal to that side, this side will be equal to that particular side. Number B, we have rectangles. A rectangle will have all the angles first are going to be 90 degrees. This side will be parallel to this side will be parallel to this other side. So we have got two pairs of parallel sides. Again, if you are to construct the diagonal, this side will be equal to this, to be equal to that, it will be equal to that. Number C, we have a rhombus. Now a rhombus is a twisted square. So all the sides are equal. This is parallel to that. This is parallel to this other side. So that's a rhombus. Then 4, we have a square. A square is a quadrilateral in which all sides are equal and two pairs of parallel lines. Then all the angles again are going to be 90 degrees. And if you are to obtain the diagonals, all this side will be equal to this, will be equal to that, will be equal to this other one. We can also be able to classify trapezia and the kite under special quadrilaterals. That is kites and trapezia are special quadrilaterals. Why do you think they are special? We said for quadrilaterals to meet the aspect of being parallelograms, we must have two pairs of two pairs of parallel sides. But the kites and trapeziums will only have one pair of parallel sides, but they are categorized under quadrilaterals because they have got four sides. So for a kite, this side and this side will be equal, this side and this side will be equal. But you'll discover that for this case, there is no single pair of parallel lines. This is meeting to that, this is meeting to this is meeting to that. If you are to extend this and you extend this, they'll meet at some point. So it has got no pair of parallel lines. Then for the trapezia, we have got different types of trapezia, like we have got the right angled trapezia, then we have got this other trapezia where this is 90 degrees. So you'll discover that with this case, we only have one pair of parallel lines. We only have one pair of parallel lines. So that's the reason that they are under quadrilaterals is, and being special, is that it has got only one or no pair of parallel lines or sides. Another key issue is that rhombuses and squares are kites also in nature. Then finally, a trapezium is a quadrilateral with at least one pair of parallel lines, as we were able to see, and therefore parallelograms will include rhombuses, rectangles, squares, and even the trapezia. So out of the four we had mentioned, we can be able to add the rhombuses and the trapezia because they consist of at least one side, which is parallel, a pair of parallel sides. We now want to look at a number of examples on how we can be able to solve questions that pertain quadrilaterals and polygons. So the most important thing to pay attention is the sum of interior angles of any polygon is given by 180 into n minus 2. Size of exterior angle is equals to 360 divided by n, so long as it is a regular polygon. And then 3 is that sum of exterior angles of any polygon is equals to 360 degrees. Then the last issue was on the issue of parallelograms. Understand that squares, rhombuses, rectangles, and parallelograms, all of them are quadrilaterals which have got two pairs of parallel lines. But we have got others that have got at least one pair of parallel lines, like the issue to do with the rhombus, the issue to do with the trapezia. We can also be able to classify them under quadrilaterals or parallelograms because we have got at least a pair of parallel lines. Example 1. We are asked, find the value of the pronumeral. Find the value of the pronumeral in each of the quadrilaterals and you should also give reasons. Number 1, we are told that this is 100 degrees, this is 80 degrees, this is 110 degrees, and this is x degrees. So this is the pronumeral that we are interested in. Part B, we have a kite. We are told that this is s degrees, this is 60 degrees, and this is 40 degrees. So that means we are supposed to look for S. Lastly, we have a C, which is a trapezia. This is 125 degrees, while that is Y degrees. Good. Now we need to now move in speed and be able to calculate the angles that have been marked with pronumerals. First, when we look at the first figure, this is a quadrilateral, meaning it has got 4 sides. And we have been given 3 angles, one of them is X. Can you try to recall how or what is the sum of interior angles of a quadrilateral? We said quadrilaterals have got 360 degrees, or the sum of 360 degrees internally. So that means when you take 80 plus 110 plus X plus 100, it should be able to give you 360 degrees. So X plus 100 plus 80 plus 110 should give us 360 degrees. 100 plus 80 will give us 180 plus 110, we shall have 290. So X plus 290 will give us 360. So that means for us to be able to find X, we subtract 290 from both sides, and this will tell us that X will be equal to 70 degrees. So the size of X in this case will be 70 degrees. And what is the reason? Angles, sum of interior angles of a quadrilateral is equal to 360 degrees. So that is the reason we have been able to use for us to be able to find the value of X. Now look at the second case. We are supposed to find the value of S. And given that this is a kite, recall that this side and this side are equal. Therefore, if you were to develop that diagonal there, then that means that this angle will be equal to this angle. The same, that is on the basis of isosceles triangle. The same on the basis of isosceles triangle on the other part, this angle will be equal to this angle. So in a nutshell, what does it tell you? It tells you that when you take now this dot and the 2 dots will give you 3 dots. That is for that upper, and also this will be 3 dots. So that tells you that the whole of this angle and the whole of this angle, they are going to be equal. And if they are going, S and this other angle are going to be equal, then we can be able to find S, given that a kite is a special quadrilateral. Quadrilaterals have a sum of interior angles adding up to 360 degrees. So the same we shall do. So this will be S. S plus S is 2S. So 2S plus 60 plus 40 is equals to 360 degrees. This will be 2S plus 100 degrees is equals to 360 degrees. Then we subtract 100 from both sides, which will give us 2S degrees to be equal to 260 degrees. And therefore, you to find the value of 1S will be 260 divided by 2, which will give us 130 degrees. So this tells us that one of the angles, which was unknown, is 130 degrees. The last bit, we are having a trapezia, and in that particular trapezia, you can be able to see that we have only been given one angle, which is 125 degrees. Then this is y degrees. I want you to extend this and extend this two parallel lines. What can you be able to recall about that line? A line crossing two parallel lines is called a transversal, and it ends up creating what you call co-interior angles. So that means y and 125 are co-interior angles. And if they are co-interior angles, we are able to say that co-interior angles, the sum of co-interior angles add up to 180 degrees. So that means if you take y plus 125, you will get 180. When we subtract 125 from both sides, we'll be able to get that y will be 180 subtract 125 degrees, which will give us that y is going to be 55 degrees. And once you have gotten this, you can now be able to get the other, angle. So the reason here is that co-interior angles of parallelism normally add up to 180 degrees. Example 2. For each of the polygon, find the angle sum hence find the value of A. Now for the first case, we have this polygon, so that is an irregular polygon. We are told that that sign is there. You can be able to recall which type of a polygon this is. One of the angle is more than 180 degrees, but unfortunate is that that particular angle is A. So this will tell you that this is a non-convex polygon. 40 degrees, 135 degrees, 100 degrees, and 115 degrees. So let's solve this first before we go to B. Now we have been asked first to find the angle sum of this particular figure, where we are having how many sides? 1, 2, 3, 4, 5, 6 sides. And from the formula, we'd say that sum of interior angles of a regular or a polygon will always be given by 180 into n, we subtract 2, where n stands for the number of sides. So that means for the sum of interior angles of this particular polygon, where n is 6, will be 180 into 6, we subtract 2. And this will give us 180 multiplied by 4, which will give us 720 degrees. So this tells us that the sum of interior angles of this particular polygon, which yes, it is not regular, but the sum, if you are to add all these angles, you must get 720 degrees, generated by the formula 180 into n minus 2. We had also said you can use the other formula of using the right angles. That is 90 into 2 and subtract 4. Now the next work on course is to find the value of A. And you can be able to see that this actually A is an obtuse angle which is more than more than 100, or it's going to be a reflex angle. Now for us to be able to find A, we now sum all these angles and equate them to 720. So this will be A plus 40 plus 135 plus 100 plus 115 plus, what does this sign mean? It means that this angle is a right angle and therefore it's 90 degrees. Then we equate them to 720. So that means that our A is going to be 720, subtract the addition of the others, which is going to give us 240 degrees. So this is 240 degrees. So sometimes you can be asked to classify this particular polygon. Is it convex or a non-convex? It's a non-convex because one of its interior angles is more than 180 degrees. Part B of the same question. So we have a regular polygon where all sides are equal. Then we are told that this is going to be B and this is going to be A. Now there are two ways in which you can be able to solve the values of A and B. Because it's a regular polygon, we can be able to find the size of one exterior angle. Then we use the property of straight lines to find the value of B. Alternatively, we can use the sum of interior angles, which is 180 into 2 into n subtract 2, where n is the number of sides, which is 1, 2, 3, 4, 5, 6, 7, 8. So that will be 180 into 8 subtract 2, which will be 180 multiplied by 6, which will have given us 1080 degrees. So the sum of interior angles is 1080 degrees. And because it is a regular polygon, then B will be 1080 divided by 1, 2, 3, 4, 5, 6, 7, 8 divided by 8, which will have given us 135 degrees. So if this is 135 degrees, you can be able to find A because the interior and exterior are forming on a straight line, and therefore A plus B will be 180. Therefore our A will be equal to 180 subtract B, which is 135. And this will have given us 45 degrees. So that means that each of the exterior angle will be 45 degrees. Alternatively, you can approach it by looking for the size of the exterior angle first before using the issue of the straight lines. And in that case, we'd say that the size of exterior angle will be given by 360 all over n. So this means it will be 360 divided by 8. 360 divided by 8 will be 45 degrees. Then after getting 45 degrees, you can now use the issue of parallel lines, of a straight lines, angles on a straight line, for you to be able to find the value of B. So this brings us to the end of our subtopic that we have been looking at today, that is quadrilaterals and other polygons. The most important thing for you to be able to recall is on the aspect of quadrilaterals. They are called quadrilaterals because they have got 4 sides. We have also talked about the size of exterior angles and the size of the interior angles. Size of exterior, the sum of the exterior angles of any polygon is equivalent to 360 degrees. Then the sum of interior angles of a polygon depend on the number of sides, and we said you can be able to use this particular formula, sum of interior angles is equals to 180 into n subtract 2. Next time when we meet, we shall look at congruency of triangles and the proof by use of congruency of triangles. Thank you.